1 bits, say there will be a carry, that carry has to be added, no? So in that sense, what we have to do is, first one will be your AND gate, because there is no carry coming from any of the previous stages. So this will be your first sum. Say if I take this as S0, S1 and S2 along with a carry sort of thing, if you have carry generated at the last bit. So this will be your result set. Now this becomes S0, and this should be implemented with an AND logic for generating the product term sort of thing. This is A1 B0 and A0 B1. Okay, now these two has to be taken into like full addition format. Okay, so I take this to an XOR, and is this half adder or full adder? You let me know now. Is this half adder or full adder what you are taking? Now this becomes S1. This is your S1. Okay. Now this next one, next stage I am taking. This is A1 B1. Okay. This will be going to one more XOR operation and one AND operation. We perform. This will be the logic of, say what we get here is S2 and this is C2. Okay, done. So this will be your 2-bit 2 into 2 Vedic multiplier, 2 into 2 Vedic multiplication. Now if this is extended to 3-bit, okay, what will be the increase in your complexity? A1, A2, B0, B1, B2. Okay, you can define these things as in these steps. Now how many terms you will be getting? 1, 2, next one is 3 terms, 4 and 5. Okay, these are like I am taking this as the logic of what are the inputs that are being getting ANDed. I am taking AND or logic. A cross indicates that it's an AND operation completed with OR logic. Okay, so for this, what is the complexity? Do you expect it to be simple as this 2 into 2, or it will be more? Huge it should be, because 5 terms we are getting. 5 terms we are getting here if you are observing there. So I'll give you that 5 terms. One second, let me take this as reference and draw it. What are those 5 terms? We'll see. Okay, first one is your A0 B0. Because in which style of modeling you are attempting in your lab? Behavior style you have taken. Okay, because this is the simplest format we are taking, like AND OR logic format, using one XOR operator and an OR logic. If you have complete circuit, you can define simple 3 components. If you are taking, you can define the Vedic multiplier to any extent. So maybe attempt one in structural style also, either your 3-bit Vedic multiplication or 4:4 Vedic multiplier. Okay, this is first term. Okay, second term is A0 B1 with this one, A0 B1 with A1 B0 getting added, and operation we are performing. This will be going to an XOR operation, and this will give you say this is S0, this is S1. Okay, now what is that we are doing here is, this is half addition we are performing. This is, this segment we can say this is one half adder. This is one half adder. Okay. Next, come back. This one. This two we have finished. Next one is third term is A naught B2. This one. A naught B2 is one and A2 B naught second term, and third one is A1 B1. Okay. So these three will be going to three input XOR operation you can use. Okay, and each will be taken as each pair of that will be taken as one AND logic. You can have this clarity if you want. Check this out. Okay, this has to be OR to get the equation. If you are not able to understand, just write these terms here if you want. Okay, and this will be going to um, here this carry will be coming. Sorry. We are taking this carry along with this carry and do one XOR operation along with what you can take is this is one input and the second input to your AND operation. I'll tell what are these terms what we are taking now. Okay, this will be given to one more XOR operation, two input XOR operation. Okay, and this OR gate will be given as the input. Now this two will be one half addition, and the two carries will be ORed and taken as carry to the next stage. This becomes carry. And this is your sum. This is S2. Okay, third stage finished now. Okay, this is self-explanatory. Once you write this equation, you can realize that what we have implemented here actually. Okay, the fourth term is A1, this one, A1 B2, A2 B1. A2 B1. This will be taken through your half adder, and this is carry generation. You have this output is taken back into another half addition, and this will be the carry from that stage. Okay, this will be taken to, see here, this is one more half addition. I'll let you know what are these terms now we are taking in, and this will be ANDed once again for its carry generation. Now these two carries will be ORed for the overall carry at that stage. Now this becomes your S3 and this is carry. Now this is carry in this stage and this becomes carry from this stage, and this is the carry from the fourth stage. Finally, you have the fifth term, which one is simple A2 B2. Okay, now this is an AND operation. Now this has to be taken, like from this carry will be added through one half addition process. This will be giving you the final what you say sum and carry what you are seeing at the final stage. Now you have this one is S1, S2, S3, S4 and C4 you need to see. Sorry. S0, S1, S2, S3, S4 and C4. Okay. Now let me give this. Now this is this segment. If you can see, this segment we call it as 2-bit. This is 2-bit adder. We are not saying full adder or half adder. This is 2-bit adder. That means full adder, if you are taking in place, this will be in place and vary from the previous stage. But this is just adding the 2-bit on inputs. So we are not saying this is a full adder, but we are using a half adder to add 2 bits coming from previous stage and the in place bit addition. Now this becomes full addition. This is one full adder and this is one half adder you are having. And now again this one also, you are taking 2 bits. Now this is your 2-bit adder. So two 2-bit adders are used. 2 half adders will be used. This is one more half adder at the beginning stage, and final stage one more half adder. That means altogether what we are taking is one full adder, 3 half adders, 2 2-bit adders. So this gives you a 3-bit Vedic multiplication. So it is self-explanatory sort of thing, like what are the inputs we are deriving. For that, what is the circuitry you are taking is self-explained here. If you have any doubts, you can ask me later also. Okay. Why the specific name of 2-bit adder is given is the bits are different stage generated bits. Okay. So that's why we are not naming it as a full adder. That is the only one point you have to make now. Now, from the 2-bit thing, when you are taking back into something like 3-bit, what is the complexity we are trying to see? Huge change in the complexity we are observing. That means if I attempt for designing a 4-bit Vedic multiplication, this circuitry becomes so huge, like a complex thing. The wiring becomes very complex. So it's better to use a 2-bit Vedic multiplier as a building block. This 2-bit Vedic multiplier, we can use it as a building block now. And from that we can generate a 4-bit Vedic. Say 4:4 Vedic if I want to define. Maybe I can use 2x2 Vedic multiplier, and I can generate this 4-bit multiplication. A1, A2, A3, B0, B1, B2, B3. Okay. Now see here. How many terms we need to get? 1, 1, 2, 3, and you'll be going for 4, 5, 6, and 7. Okay. So that becomes like very huge. Like if you go on doing this type of circuitry, it becomes very uncontrollable sort of thing. We may not be able to understand what the things are happening there. So instead, I can take 2:2 Vedic multiplier, and I'll use 4 2:2. I'll mention what are the bits that will be taken. 4 2:2. Now, first 2 bits here I take is A0, A1, B0, B1 I take, or else I'll take another color. Let me take this color. A0, A1, B0, B1. And next one here I'll take another 2-bit, A0, A1, B2, B3. And here another 2-bit I'll handle, B0, B1, A2, A3. Next here one more set of 2 bits, A2, A3, and B2, B3 I'll take. So this way we try to distribute the data of this 4 bits. And now here you'll be getting 4 outputs. 4 outputs in the sense you are getting this one S0, S1, S2, S3. That 4 outputs I am mentioning them as 0, 1, 2, 3 say. 0, 1, 2, 3 outputs. Now for this, I'll use one more set of what is a 4-bit ripple carry adder. Do you remember this ripple carry addition? 4-bit ripple carry adder. The basic level of adder. I think no one is there, just you have logged in and enjoying. Huh? There won't be any quick answers I'm getting.
No, ma'am, listening.
Yeah, this is Q0 and this is Q1. That means I'm taking the quotient sort of thing. Or little bit, if there is a confusion, let us take this as S0 and this will be the final S1. S0, S1 will be directly coming at the first stage of 2-bit Vedic multiplication. And the next set of these two, the 4 outputs what we are getting here will be taken as the inputs for one 4-bit ripple carry adder. As simple as this, like you're taking the complete addition on this 4 bits using one set of ripple carry adder. Now this will be giving you 4 outputs, and that will be taken along with the previous stage MSB bits, 2 MSB bits, and this is given to one more 4-bit ripple carry adder. And here see, this one 0 1, that means the lowest bits will be taken as the previous MSB bits. Okay, and here the other 2 bits will be grounded. These 2 bits will be grounded, 0 0, it will be taken. Okay, now this will be giving us 4 outputs, and this, out of this, the first 2 outputs will be the final output of the process. Okay, next I'll show this. Need this bit actually in the process of addition. This will, we won't get this value, so this is grounded, this carry will be taken, and the final value what you are getting here will be 3 4. This will be your final carry versus, say, you can say, you can name this as any number what you want, the final carry, and S4, S5, S6 and S7 sort of thing. So these are the like terms what you are getting. So this is anyhow, we have this ripple carry adder as a building block already in our design. So it's an integration, or what you say, it is 2:2, 4:2, and 3 4-bit ripple carry. If you take, you will be able to perform 4:4 Vedic multiplication. 4:4 Vedic. That is so simple. Maybe if I ask you to write a code in behavior style for this 4-bit, what is the like size of your code? You have to define plenty number of inputs, no? Combination of inputs you need to define. That means comparatively for Vedic multiplication, structural style will be very simple. Like component wise, only 2 components you are taking. And for 3-bit Vedic multiplication, it is XOR, something like half adder, full adder, and an AND gate operation. So attempt using a structural style for Vedic multiplication in your lab. Okay, I'll take the next topic, that is our FPGA designs or FPGA system designs and all. How many of you have started the theory, able to understand them? What is FPGA? It's now a simple explanation is not needed as what is FPGA. What is the full form? Okay, something like we can say that these are of arrays, and how you program them is the basic question. Now, why do we need FPGAs, or what is the use of these FPGAs? What is alternate for FPGAs? Like antonym sort of thing we can say is microprocessor. What is the complementary element or complementary thing for FPGAs is microprocessors. What are these elements now? What for we are using them for programming or for designing or for implementing a hardware, like before prototyping, or what you say, before the product is released into the market, we need to test them. Okay, some portion of testing already we have learned. Okay, like when we are testing, is it physically needed to develop a sample, that means prototype, rather I have any other alternate that I don't develop the prototype, but still I am able to test it whether it is working or not. Okay, normally using microprocessors means we need to write a program, we need to write the instruction sets and all, and we have to analyze the output step by step. Like it won't be given as a hardware format, but if you take FPGA, we are developing is what you say, a prototype which directly you can put it on a base and you can generate it as a design, physical design into the market. Okay, so I can say that these FPGAs are an intermediate tools, or what you can say a standard chips sort of thing, where you can dump, or your testing can be done on you by initiating the logic parameters. Here we are not taking the what you say, code format sort of thing. We are not giving that as an instruction format. Here we are taking the logical parameters. Okay, something like we can say that microprocessors, they can be used in variety of environments. You can use them. Okay, but when you are using this, they need some software for implementing a function. Means a code is needed for them to be implemented. You can variety of applications you can use the microprocessor, but for testing we need a specific code. That means the software is must and should for testing, or what you say, for implementing that function. But whereas for FPGA, we try to take the logics or something like a Boolean format sort of thing, or what you say, a interlink of the logic gates or logical blocks we try to do, and we try to see what are the physical responses for that design. Okay, but comparatively, what is that we can say, like a disadvantage sort of thing, we can say drawback sort of thing when we implement microprocessor is this FPGAs are little bit slow in the process of evaluating the output compared to microprocessors. And not only that, the power consumption will be more. The power consumption will be more. It is slow in speed, power consumption will be more, and cost also comparatively it will be more, like with respect to microprocessors if you take. And like these FPGAs are not developed for a specific function, we can say. It is general. I can manipulate as I want. Okay, they are standard chips or standard blocks. I can manipulate them according to my need. That is one flexibility what you have in your FPGA. Okay, that means they are like you can program it as you like, and it is not a particular function or what you say dedicated logic. It won't be having. You can reprogram or you can define the logic, that sort of thing. That means flexibility is there. Okay, and this is something like what you can say programmable element in your design. Like why do we need programming or what you say readjusting the things? Programming is nothing but until what I want, I need to change the design. That means until my specifications are like we reach the specifications, we try to redefine the function or we try to redefine the logical circuits. Okay, that means we need to program. We have to have the flexibility of redoing the design until and unless the function is approaching the specifications. We may not be releasing that into a prototype or a design into the market. So the FPGAs are the best tools for testing, we say. Okay, but however, there are many compensating advantages when we compare these FPGAs with the microprocessors. These are the things what we are saying, something like drawback sort of thing. But we have some advantages. Why? Because is FPGAs are the standard parts, we say. They are standard parts of the design. That means this design can be programmed and it can be tested immediately. That is, it is there won't be any waiting time for obtaining a chip, working chip, and before the design is released into the market, we will be able to have a prototype readily available by programming the logic on FPGA, and they are a simple prototyping vehicles, we can say. Prototype vehicles also we can call. FPGAs are prototype vehicles. Okay, where they can be used in the final product, and directly after testing you can put this put as an end product without any much variations in the design sort of thing, because already when you are satisfied with the result, there won't be needing or in need of doing much changes or corrections to the design. Directly you can dump it as a IC or a hardware that can be released into the market. Okay, this can be used in very varied environments also. As microprocessors, we said we can use in many applications. This or FPGAs also you can use, and like with less cost we can test. That is one advantage. Comparatively less cost we can physically, if you take a hardware, it will be very costlier for testing. If you take a physical hardware, it will be costlier. So if you want to reduce the cost of testing, maybe FPGAs becomes the best tool or what you say best element. Okay, and before these FPGAs are into the market, we had something called as PLDs and all. In the PLDs, PLAs, you have learned this. What are PLDs and PLAs? Programmable logic devices or programmable logic arrays or programmable array logics. What are these things? Are they memory elements? Are they logical blocks? Learned this? No. Both the sections. Both the sections. Both the AD sections you didn't learn? SRAMs, DRAMs, EPROMs, ROMs, EEPROMs. These are new. These are new for everyone. Quick answer, please.
We didn't learn this.
In B section. Okay. Something like basic idea is there for you then, like how you will be able to enter the data. Is that known? Basically, they are all memory elements. That much you know at least. Yeah. So how do you enter the values is changing the type of memory. Okay, that's why we are characterizing that as SRAM or DRAM or program logic arrays or programmable array logic sort of thing. So something like if you want to define completely how we are addressing them or how we are storing, we can characterize them as RAMs or ROMs. Okay, what is the difference between RAM and ROM? This RAM and ROM. This is your one type and this is one type. We can say. RAMs are volatile or ROMs are volatile?
RAMs are
RAM.
volatile.
Okay. Something like if I want to have an addressing element, okay, say this is how we are storing the data. It will be characterized into S indicates static, D indicates dynamic. SRAM or DRAM. RAM is a memory element, okay, random access memory. How we address them is different now. And what is the way we are trying to store the data is characterizing them into SRAM and DRAM. Okay, static RAM and dynamic RAM, if we can see, the data here will be stored in the form of a D flip flop. Normally, a D flip flop is a storage element, a registry. And here, this dynamic RAM, the charges will be accumulated. Sorry, charge accumulation. This is the basic difference what you have. How you are storing the data is SRAM will be using D flip flop, DRAM will be using a capacitor which will be storing that bit cell. Like the name what we give is bit cell. Okay. It is here how we are storing is it is a D flip flop element, and how do you write this is we have one dedicated write signal on the memory element or SRAM we say. When this is true, it will be written. It write operation will be done. And if this is false, it will be read operation. Like only one element we are trying to use, one control signal will be used to write or read the data. That means when write is true means you are writing something onto the memory. When it is false means you are taking the value that is stored from this to your registry level. Okay, memory to registry transfer will be done. So this is something like what you say, as long as power is on, this information will be stored there. Okay, as long as power is on, that information will be stored. For DRAM, the bit value will be stored as a like a tiny capacitor charging and discharging. Okay, this dynamic storage cell will be smaller than this static RAM because this is simple capacitor compared to big flip-flop is huge in size comparatively, and this will be allowing 4 times high storage than the static RAM. DRAM will be having a capacity to store 4 times more than SRAM because the size is very less compared to D flip-flop. Okay, so that is one typical advantage you have between your SRAM and this DRAM sort of thing. And what is the biggest or what you say huge data element available is 32-bit static RAM is available in the market. Okay, now how do you address this? Like, this is very huge. How to address say 32-bit storage element is there. Now, whenever we need to put the memory cells, we won't be putting that in single line. Something like 32 means 2 power 32 means what is the size, how many bits you will be having, or how many combination of arrays or nodes you will be getting. 2 power 32. If you put it in a single line, it will be very lengthy. Now, instead, I put that into the rows and columns. I can accommodate the space which will be taken will be what you say condensed, compressed, we can say. Like this compression, if I am doing this, we call them as array. Okay, we are putting that into row and address form. This is becoming an array sort of thing. And this array, if I want to address or something like each location will be one memory location, say. Each will be having a row and column address. Say if this is column 1, C1, R1, if I say. This is R1, C1, and this is R1, C2. This is R1, C3 sort of thing. Just for understanding I am giving. Say R2 is there. This is C1, R2. That means each combination or each one address is specifying one specific address location. Now, as this, I need to have the address of the row and the column. In order to reach a specific location, I need to have a row and column address. So this 32-bit address, or what you say, memory address, we try to allocate few bits for addressing row and few bits addressing for column. Okay, say I have B0 to B31, say. Sorry, not 31. Say I'll take, it depends on how many array bits you have. Say I want to implement 3m into 2. What is m? 3 million words into 2. You know this calculation? Say, let me have, say 12 pins are there, say, or 12 pins are there. How many cells you can handle? 12 inputs or input pins are there, say. How many cells you can handle? I think it will be 2 times of 2014, that is 4096 cells. No? Yes or no? To power 12. Is okay. One. Wait. How many? 4K means I can arrange them like here. This specification containing how many is 4K 1-bit words it will be having. 4K into 1-bit words it will be. Say if I have 1K into 4, reverse I am taking, say, RAM. This will contain something like 4K cells only. And each cell will be organized as 1024 4-bit words. Sorry. 4-bit words it will be arranged. The arrangement aspect I am explaining 4 bits. Okay, so something like if it is 64 is to 64k is to 1, if it is there, say how many it requires address bits, how many address bits it requires, 16 address bits it requires, 16 address bits it will be requiring. Okay, and say something like 1m into 1, if I'm taking, how many it will be, huh? 16 address bits for addressing 64k into 1. Because 4k into 1 RAM means 4k 1-bit word it will be. 64 means 16 address lines I need. What is the size? You can expand this and see. 64 into 1024 you have to get. Say 1M into 1 bit RAM is there, say. It needs 20-bit address bits. So likewise, say what is the size of the RAM, that many number of address bits will be needed. Okay, so it is something like we can say it is time multiplexed. These are time multiplexed addressing memories. Like two-dimensional we try to take. It will be row and column we are considering. So this will be two-dimensional sort of thing. Having row and column address. So something say as simple as this. I want to take or design something like 3m into 2 RAM, say. How many bits are needed? I'm saying this is 3 million words, each of 2 bits per word. That is the meaning, 2 bits per word. Okay. Now, how can I take this is, I can put this as 3 1m into 2. Got this? I can reorganize this as something like, see here, I can put this as 1m into 2. 3 1m's if I take. 1m into 1. 3 1m into 1 if I take, and I try to put this into 2 rows. 2 rows. Able to understand what I am saying? Directly I am not taking 3m into 2, rather I am splitting this as 1m into 1, 1m into 1 and 1m into 1. This is 3m now, 3m into 1. Completely this is 3m into 1. But what we are trying to design is 3m into 2. So repeat this 1m into 1, one more row. Now you will be getting that as, this is 3m into 1. This is one more 3m into 1. Combine them as a row and column. What you are getting is 3m into 2. Able to understand how we are organizing them? Okay. So each memory should be having a, what you say, data input sort of thing and data output sort of thing. For what you say, writing and reading. Read and write operation, there should be input and there should be output. There should be input and there should be output. The same thing happens here also. Input versus output, input and output, input and output for specific read-write operations. Now, what are the other things that are to be common? Say, if I try to take them, this is my input line, this will be common. Okay, and this will be my output, say this is output line, common. This will be output, data in then data out. And What are the other things we need for them is your operation of write. I said, no, if write is true, it will be writing. If it is false, it will be reading. And what address location it has to read or write will be specified as address thing. So each element will be having the address and the write signal, write and address signal, write and address signal, write and address signal, it will be happening. Now how to access them is, now if you are supposed to use this as 3m is to 2, this control signal of write should be common. So it will be taken common to the two segments. So this will be a write signal which is common. Now this makes it as 3m is to 2. And what is the address on which you are writing or to access the read or write will be given as the address input. And this address input something like should be in terms of row and column address, and this row and column address again should be common to, sorry, all the bits. It's I into another line. This is address, and this is address. This is your address bit. Okay. Now again here you have this D in and D out which is common, D in and D out which is also common. Okay. What is that you are writing? So this is D in and something like input and output, D output. Okay. Now how to address them is something like every, like you, if you can take this is what we call them as banks. This is bank 1 of 2-bit. What we said here, 3 million words of 2-bit words, 2 bits per word. So this is 2 bits per word, and it has 3 banks because this is 3 million, 3M now. So bank 1, bank 2, bank 3 we can say. So each bank will be having a chip enable, and this chip enable is common. And here also chip enable, this is common. So each bank will be having a common chip enable. Okay. So this will be addressed by, say, bank enable signal 0, say. If this is bank enable 1, and this will be bank enable 2. Now, for this, how many bits we need is 22 bits. For 3m is to 2, we need 22 bits. So 22 bits, how we'll be organizing is, say if I am taking this as B0 till B, say 20 and B21. 2 bits will be taking for, because we have 3 banks, we need 2 bits for addressing them. Okay. So 2 bits, last MSB bits will be taken for bank enabling. Okay. And the remaining until B19 to B10 and B0 to B9 means 10 plus 10, 20 and 20. Okay, 22 bits complete. These are 10 bits, these are 10 bits, and these are 2 bits. So 22 bits are given. First MSB 2 bits will be for bank enable to address 3 banks. Okay. And this will be, the next set will be the column address, and least significant 10 bits will be taken for row address. Okay. Now, how do we enable this? We need a decoder for this. We need a decoder. to decode which bank is enabled and which row and which column address we are trying to access. Okay, so this decoder, if I can take, the decoder uses this B20 and B21 bits for enabling how many banks we have. B bank enable 0, bank enable 1, and bank enable 2, and this is 0 because we are not having fourth bank. No? So this will be not used, no connection we can say. And using this decoder, we will be decoding which bank we are enabling, and after that, which row and which column will be enabled is given by the next 20 bits. So this way we are trying to, access the RAMs. Okay, and these are something like time multiplexed, we are saying, because the row and column address will be decided which memory location we are trying to access. So this is something regarding your accessing of RAM. With chip enable, you will be addressing the bank, and the row and column address will be addressing the exact address location, and the operation of write will be performing, or write will be deciding where if it is false, it is read, and the same thing. If it is true, it will be writing. So these two operations along with the enabling signal, it will be performed. But contrast to this, we have ROMs. Contrast to this, we have ROMs. ROMs are something like firmware or userware programmed. You can have two types of ROMs. Okay, something like firmware is something like pre-programmed. This is pre-programmed, we can say. A simple example I can give you is a calculator. If you have, okay, say in the calculator you have many functions. No, are you defining the functions yourself, or are you using them? Are you defining or using? Say sine theta, cos theta, add, subtract, multiply, all these are functions in your calculator, no? And are you trying to use them or design them?
Use.
Use means there should be predefined operation, no? So that parameters will be predefined by the factory end firmware, and you cannot manipulate them. Just you can use them as a input given, output taken sort of thing. Those things are firmware ROMs, we can say. That means you cannot reprogram them. Okay, but userware sort of thing or customer end programmed elements, if you have, like you can use them for generating your own logics. Userware, you can generate your own logics. That means you can program this. How many times you program depends on what is the type of ROM you are using, or how many times you are able to program will be classifying them into like something like PROM sort of thing, EPROM sort of thing, or EEPROM sort of thing. Say PROM is programmable read only memory. PROM is like once you can program it. Okay, at the user end you can program this, and how you will be able to store the data. What the format you are storing is either 0 1 values only you can store, no? So the this will be having microscopic metallic or polysilicon chips or fuses, we can say. They'll be having polysilicon fuses, and you have to blow them out if you want to store like 0. The user has to blow the fuses for selecting a 0 on their bit location. Blow the fuse, it will be 0. You don't blow, like it is as it is intact means it will be storing 1. In PROMs, you blow the fuses, it will be 0. And EPROM, the other type of memory is EEPROM. EEPROM means erasable, programmable, read-only. PROM means programmable, read-only memory. EEPROM is erasable, programmable, read-only memory. And now how many times you can reprogram this? We are saying erasable, we are saying. For that, say something like here bits are stored as electric charges. The value will be stored as electric charges. Here these are fuses. For PROM it will be fuses. Okay. Something like if you want to store a what you say 1 or 0, here the bits will be stored by electric charges that will be trapped on silicon. Again we are taking the semiconductor thing only, and when you are erasing, what happens here will be reverse. You erase this charge, erase the charge, it will store 1. Here you blown the fuse, it will be storing 0. Here you erase the charge, it will be storing 1. Okay. And if you want to write back 0, back you want to write 0, what you have to do is you have to put this into high voltage. This silicon chip you have to put or expose that to high voltage, and that will be making it as a conductor. So it will allow the charges to accumulate on silicon if you are exposing this to some high voltage. Okay. After this high voltage is removed, the trapped charges will be remaining there until and unless again you program it for another time. Okay, erasing program if you do, then again you can redo that charge as 1 or bit value as 1. So PROM and EEPROM are a little bit complementary in their storage process. Erasing or storing 0 needs fuses to be blown out, whereas for 0 you have to make the charges to be accumulated on the silicon chip. Okay, when you erase, it will be storing 1. That is the difference you are having. And see, this erasing you can do for not many number of times, EEPROMs. Only fewer times it will be allowing. Okay, you cannot repeatedly do this thing. But one more thing what we have to do is when I want to put or expose this EEPROM or to an electric high voltage, I need to remove this from chip or remove from the design. I cannot put this on my design and expose that to the high voltage. It will be spoiling the other gadgets or other devices. So when I want to do a charging or discharging sort of thing, I need to frequently remove the memory from the design and do the process of storing either 1 or 0. This is disadvantageous. Every time we cannot remove that from the circuit and do the things. So instead, what we have is EEPROM, electrically erasable, programmable, read-only memory. That is EEPROM. That means this can be without removing physically from the design, like you can directly store the data of either 1 or 0. Okay, so the sequence of 5 volts will be given to the program. Like here, there will be a specific program designed internally where if you expose this to 5 volts, it will be able to write the data in. Okay. Now the erasing process will be done without removing that from the circuit. Directly, you give an instruction or 5 volts applied to that program, it will be giving a value of 1 at the needed location. So that is one advantage you have when you compare that to prompts. Now, another format or what you say, we don't want to again and again redo the Boolean equations. Already we want to have some set of predefined functions available that will make my design simpler. then what are the things we have is the programmable logics we have. Programmable logics. Now that is your PLDs or PLAs. Okay. The term programmable here means that the functions can be specified after the chip is manufactured. Here, the functions can be specified after the chips are manufactured, something like this. Say, I want to have a Boolean equation, something like this. Say, A dash B or B dash C sort of thing is there I want to implement. Now, I need an AND logic, two AND logics, one OR logic. Now, if I have a specific, predefined combinations of these inputs, say what I want to have here is A should be present in A or A complement format. Sorry, this is inverted. A complement format. B should be in B and B complement format. C should be there in C and C complement format. Now, I can define the and or combinations by doing a fusing now. Okay, when I want to implement this, what is the logic I want? One AND operation I want. So I try to take a fuse of A dash B. This gives me an AND logic. Another one. This is B dash C. Now this is one more AND logic. Okay, these type of AND operations I will define, and if I take a horizontal wiring, this is OR logic. Able to understand this? We have all the inputs available in its true and complement form. A vertical wiring which is having the fuses. If you want to have an AND operation, you do the fusing here. The others will be open. Though you're having an intersection, the others will be open. Which one you are fusing will be forming the AND logic, and the horizontal fusing will be OR logic. This is the way we try to define this equations, Boolean equations. So these type of programming is called as PLA format, programmable logic array formats, because these are in array elements. We name them as array formats. Okay, but here, see, both your AND operation and OR operation you have to define. You are defining them. Okay, and like something like it depends on what is the Boolean equation or the logic you are implementing. That many number of fuses you have to define, and you will be taking that as programmable and programmable OR. Both are programmable elements you are taking. Okay. Now, the more the inputs, the bigger size of the array you will be getting. The more the inputs, the bigger size you will be getting. Now, this has to be taking much huge area if you are going on increasing or adding the number of inputs. Okay, that means you are increasing the product terms and you are increasing the OR terms also if the number of inputs are increased. Now, so something like I have predefined product terms available. Still, my job will be easy. Here, we are defining these product terms and sum terms. Instead, I have predefined product terms and I need to program only one segment. Then it will be very simple for implementing any huge complex circuits or Boolean equations. Something like those we call them as PALs. PAL is nothing a friend sort of thing. We can synonymically say this is programmable array logic. In this programmable array logic, what is the difference between PLA and PAL is here, this is two-stage. Okay, sorry, two-stage, where first stage will be the AND logics which are fixed, and the other one will be, second stage will be OR logic which can be programmed. according to your equation. Okay. PLA means both and or has to be programmed. This has to be programmed. That is a major difference you are having. That means something like this. Say if I'm having with three inputs sort of thing, all possible what you say product terms will be available as something like this, like you will be having, say, based on these are our inputs we are having, every term will be taken to your AND gate, something like this, having all terms in every possible product format. Okay, product terms will be readily available for us. How many you have, how many are possible will be there as AND logic. Now this is fixed now for us, and there will be AND or operation. Now how do you perform your Boolean equation? Is these inputs will be like whatever the terms you are using will be kept intact. The others will be blown out. Say I'm taking A dash B sort of thing. A dash B means C should be blown out. So C fellow will be blown out and A B combination only will be kept. So in that sense, you are now trying to use generate that Boolean equation based on the logic, and you are trying to take the fuses which where that input is not available in your product. Okay, so something like this is very simple when compared to your PLA, because only the fuses has to be blown out for the terms where the inputs are not being used. So many type of PLAs and PAs are available. Something like 18L4 is one PLA, say PAL, not PLA, sorry, PAL. It says that L says that it is you can say logic low, active low, active low. L indicates active low. Okay, 18 indicates the number of inputs. Sorry, outputs. 4 indicates the number of inputs. Is the meaning that. Like the specification wise, L will be signifying that it will be outputs will be active low. Okay, it has 18 pins. Okay, and it will be having 4 outputs. That is the meaning. Say normal in market what format you will be giving the specifications is PAL 18L4 if it is given. This is AND gates you have, which is programmed, and have 4 outputs out of this 18 pins available. That is the meaning you have. So many type of PALs are available in the market. 16 or 8 PAL is there, say. 16 or 8 means it is having registers. That means this fellow indicates that there will be D flip-flops in your design. That means they are 8 D flip-flops and 16 pins. 16 pins. So how many number of AND logics you can develop using them will be given as input to 8 D flip-flops in the registry. That means wherever design you want to have some storage, feedback is needed. Something like your sequential designs, if you want to take, you can use this type of calls, having registers. Only L is indicated means L is indicated means only you'll be having AND OR logics. That is the difference you have. Okay. These are a few types of memories that we have in the market, and everywhere you are supposed to address that as the row column addresses, and based on your logic you are trying to define the circuitry. what is the logic implementing there. Now, here in your FPGAs, coming back, your FPGAs, they'll be using these SRAMs. And SRAMs are, as we said, two-stage. And these SRAMs are two-stage with the AND logic being fixed and OR logic being operated. You have to define your own logic. So maybe as a FPGA element, like compared to the advantages with respect to your microprocessors, these designs can be tested very simple. More waiting time won't be there for the product to be released into the market. Waiting time means actually from one design to another design. If you want to generate a successful product, there should not be much gap. What happens if there is a big gap between the product released into the market? You'll be losing the, what you say, vendors thing will be gone, and your business will be down. The customer will be choosing another vendor or another product which is having much benefits than the previous version of your design. Okay, so there should not be any huge gap. Much gap should not be there. That's why our gadgets will be updating very frequently. New models will be released into the market. So for that, we need to have one testing before it is released into the market. So FPGAs comes into rescue for us now. So what are the elements that are giving us a good, what you say, testing environment? Is something what we have seen is your BIST architectures we have said, and the controllers to test them are seen. I think you remember them now. This BIST with the tap controllers will be again used along with SRAMs. All together, if you put, this makes your FPGA. And here we are using some anti-fuses sort of thing. Okay, when you want to program them, we are saying these are two-stage things with the AND OR logic. No, we are using an anti-fuse technology for programming the values of zeros or ones in your FPGAs. Okay, and these FPGAs are something like they will be used as glue logic. What is this glue logic meaning is it will be connecting more segments. Say, in my design, I have huge complex segments, and now I want to test them sort of thing. I can use an FPGA which can connect one of the circuit to the other circuits. Okay, so this can be FPGA can be used as a glue logic, we are saying. And this PLDs will be used as a prototypes, and they can be directly incorporated into your final design. And you can have like the more the number of inputs, the denser the PLDs will be. So instead, we will be having that limitation, like two-level logics only. We have to limit ourselves. If more number of inputs you have to implement, maybe other aspects we have to see is how much of circuit complexity is there, how much of wiring is there. These all the things will be deciding the size of your FPGA or the type of FPGA what you have to use. So the basic characteristics of this. Hello. Yeah. Okay. Yeah, yeah. Yeah, I didn't observe the timing. Okay, so I'll stop here. Like, we need to actually address three elements for us for FPGA. What are the interconnects? What are the input pins? And what is the architecture? These three, if you learn, that is enough. Okay, next year I'll complete that. Okay, abstraction, like your input output pins and configuration. This if you learn, that is enough. Okay, I'll stop here.